So Roger, how did you get started in all this? I want the full story, because you've been making mirrors and working up in scale for a couple of decades now. But how did it all start?
Well, I think I'd always been interested in the sort of instrumental part, both in physics and then when I moved into astronomy. So when I first came to Arizona, I was building instruments to use on what were then big telescopes here, 2.4 meter telescope.
I know, I used your polarimeters when I was a grad student.
So that was fun. And then when I came to Arizona, there was the project to make the multiple mirror telescope, which was a telescope with small mirrors, just 6 foot diameter, but 6 of them. And that went pretty well, and I was involved a little bit in getting that online and making it work. And the amazing thing about that was that we found that it made very sharp images, better than any others probably in the continental U.S. And we figured out, or my colleague Nick Wolf figured out, that this was because the mirrors weren't the conventional slabs of glass that people have been using, but they were surplus from the Spy satellite program, and they were thin honeycomb mirrors. And this had a sort of unexpected side benefit, which is because they were lightweight, they cooled with the night air, so that the mirror through the night stayed at the same temperature as the air. And this meant that the normal kind of convection coming off the surface of the glass, which spoils the images of telescopes, that was eliminated. And so the telescope was making sharp images.
And people sort of forget, but it seemed like big mirror making was reaching a limit. I mean, the 200-inch, I've been there and observed there. It's a huge cathedral-like dome and a huge mass of glass and telescope structure, and you figure scaling that, it's not doable.
Right. So our thought was twofold, that if we could make a telescope from 6 small mirrors that made very good images, it's certainly possible to make mirrors bigger than 6 feet in diameter. So we thought maybe we can make a telescope that has a bunch of mirrors of a bigger diameter. But we wanted to make them with this lightweight honeycomb structure.
And you also were making them fast. The optics were faster than traditionally had been used.
Yeah, well, at that point, I haven't made anything.
Oh, okay.
But certainly in thinking about if you want to go to the next generation of telescopes, probably the most expensive thing maybe in the Palomar telescope, surprisingly, is not the mirror or the steel. It may be the building, which is huge.
Right.
It's cathedral size. And so if that were going to scale and even bigger cathedrals, that would make these big telescopes very expensive. So the way to overcome that is to make a mirror which has a very short focus relative to its diameter. So, for instance, on the Palomar mirror, the mirror is 5 meters, or we need to turn that into feet.
18 or
18
so.
feet. Okay, thank you. In diameter, but the focus is formed 3.5 times that distance above the mirror, so 50 feet above the mirror. And as that swings around, it means you have to have this very big enclosure. So if we could make mirrors that brought the light to a focus, very closely above them, maybe the same distance as the diameter of the mirror, then you could turn such a telescope in a very small building. So those were thoughts going around our heads. And so we wanted to make bigger but lightweight mirrors, and nobody could do that. And so with my student here at the time, John Hill, we looked at ways to mold glass not simply into a slab, but into what's called a honeycomb structure. This is a very common structure in industry and in nature, where you have the surface is two thin sheets, and then between those two sheets you have a lightweight rib structure. So, for instance, bird bones, which are designed to be light or have evolved to be light and stiff, are made with this structure, and so are doors and many other things. So, how do we get glass into that structure?
Oh, just as an aside, I want to know if it's apocryphal. I've heard stories like your wife Eleanor, you messed up her waffle iron trying to make honeycombs.
Well, it's almost right. I did start to try and figure out how to shape glass. The first thing I did was to melt some glass at home, and I did not actually steal the Pyrex glass from the kitchen. I went out and bought some, and I didn't use the kitchen waffle iron. I think originally, though, I used a heating element which was sold as a replacement for your electric kitchen stove. And I did melt some glass with that together, and that got me thinking that maybe this was possible. So with my student, John Hill, we worked out a way in which you could actually melt glass and let it run into a mold. But instead of being simply a cake pan, right, that would give you a solid disk of glass, it was like a cake pan, except screwed to the bottom. We had a lot of blocks so that the glass would fill the pan, but it would run around the blocks. And later, we could take those blocks out and leave a lot of voids in the glass. And that way, you could make a thick disk of glass, but it would be 80% air after you've taken the blocks out. So that would give us the lightweight, stiff structure, and also a structure that we could ventilate so to control the temperature during the night. So the first mirrors we made like that were 2 feet in diameter, and then I knew at that time that what I wanted were mirrors that were 25 feet in diameter. So over the years, we had a program of making mirrors of ever bigger diameter. So we went from 2 feet to 4 feet to 6 feet.
And these were just a series of staged rotating ovens. I mean, the technique didn't really change. It just kept scaling up.
Yeah, within just a very few years, when we made the first 6-foot mirror, we'd settled in on a size for the blocks and a thickness for the glass and so on that we've kept with ever since. And it's not because we just run out of good ideas. I think in trying to design these mirrors and to get the structure right, when you come to a honeycomb sandwich structure, that is the most efficient structure you can put a material into to make it stiff and lightweight and thermally responsive. And of all the materials you can make that structure out of, the type of glass that was used at Palomar is in fact an optimum in the sense that it's a glass that you can melt into a mold, and it has very low thermal expansion, so it won't distort its shape. It's chemically very stable, which is why it's used in the kitchen, because it lasts for many years without getting messed up. So I modestly think now that our mirrors made of this molded borosilicate, is the general term, glass, have an optimum structure and an optimum material. That's why after 20 years we're still making the same thing. And I like to think that if there are aliens on another planet who are looking at our planet,
right,
that they may in fact be using telescopes that look just like this.
Yeah,
because the same rules of structures and chemistry apply across the whole universe.
Convergent evolution.
Right,
yeah.
Exactly.
Now, it seems like when you do these kind of engineering projects for the first time and then scale them up, there's a certain amount of experiential engineering going on. You're sort of, I mean, not quite seat of the pants, but you're figuring things out as they happen and evolve. So that must be an interesting aspect of doing this kind of work, because each time you scale up, you're doing something no one's ever done before.
Yeah. So what the general strategy is that you use all your knowledge of physics and chemistry and whatever. So the experiments are always, you're trying to do it the best way that you figured out on engineering grounds. But always when you actually do something or make something, Mother Nature has something to teach you. So, in fact, we went in this very steady progression, and each time we made a bigger mirror than we'd made before, we learned some new tricks that you needed to sort out. And it's still, when I sit back, now we're casting mirrors which are 27 feet in diameter, and they have a lot of rib structure, where the ribs are only half an inch thick. And the fact that you can get all this out in one piece, and touch wood, we haven't had one of them fail yet. It's pretty remarkable. This is a huge structure, and this is glass, the same stuff that it's very easy to break and crack and so on.
So you touch wood there, and you don't have to divulge any secrets, but there must have been some twitchy moments. What have been some of the twitchy moments where you just weren't sure how it's going to work out, or what it were? Well,
the twitchiest moment probably was at the first time we tried the full-size 27-foot mirror. And one thing I should explain is that the sort of cake pan that you melt the glass in, the walls of it are made like a barrel. So there are staves, and those staves are held together with bands like a barrel. But when you heat something up by such a huge amount, there's a lot of things expand differently. So the bands around the barrel actually expand a whole lot more than the barrel does. So if you don't deal with that, it's all going to fall apart. So we deal with that by pulling on the bands from outside the furnace. So we have metal bands, and the tails of these come outside the furnace, and we pull on them. Well, the first mirror, we weren't pulling hard enough. So when the glass melted and the pressure of the liquid glass is felt by the walls, then it actually opened cracks in the wall, and the glass ran out, or some of it ran out.
Wow.
Not 2 tons ran out, but the total amount of glass was 20 tons, so there was still a lot left. So with that mirror, once we realized what was going on, we quickly cooled it to freeze the glass, and then we cooled it slowly to room temperature, and then we tightened up the bands and cleaned up the 2 tons of glass that had leaked out, and reheated it, and we put in the extra 2 tons of chunks on the top, and we're actually able to recover that mirror. And it's now one of the 2 mirrors in the Large Binocular Telescope, which is the world's biggest telescope.
Yeah. Now, what about the sort of past the peak temperature and you're in the annealing phase? There's still things that can happen. I mean, presumably you worry about bubbles, and I mean, you've just stirred up a large amount of material and hope that it's all going to settle uniformly.
Yeah, actually, we don't. It used to be in Palomar that they would get hot ladles of a ton of glass at a time and pour it into the mold. We actually use sort of chunks of glass that are broken out of a pot of glass, and we just stack in the 20 tons over the mold, cold chunks of glass, and heat that up together, and you would imagine that a lot of bubbles get trapped when it all melts together. In fact, the mold we deliberately make out of a material that's porous to the air, so that anywhere the air comes to the surface of the mold, it gets pushed out. And then we wait, watching with a TV camera for several hours while the glass is hot. And you actually see the bubbles coming to the surface, and they break in slow motion. So the whole process of a bubble coming up and breaking may take 20 minutes, but they do eventually go, and we end with a nice smooth surface.
Right. Oh, and talk a little about where the glass comes from, because you talked about small pots, and it's almost an artisan level operation that produces this vast amount of glass you need. How did that come about?
Right. Well, in the 19th century, when there was a big development of optics and glass, one of the breakthroughs was figuring out how to stir liquid glass to make it uniform and pure and get the bubbles out. That was in Germany. And the pots that people melted glass in were made of clay, and you maybe melted something like a ton at a time. And that's exactly how our glass is made. So it's made in clay pots just the same way that it was pretty much 100 or 200 years ago, and it's stirred to get rid of the bubbles.
And it comes from Japan, is that right?
The melting is done in Japan. Last time we checked, I think the sand was coming from the white beaches in Florida. So,
okay.
But yeah, the company that makes the glass in Japan, but compared to people that make glass for bottles or architectural glass, this is a tiny fraction of the volume. So it's a specialist thing. So we buy about 20 tons a year of glass from Japan. And I think we're their only customer for this particular type of glass.
Mm-hmm. And you've been to the place where that's made? Have you seen all the parts of the process?
No. One of our staff people went there a long time ago, and we saw the process. The company, O'Hara, their folks have been out several times, and they enjoy seeing their glass being used for such a big thing. Most of their glass goes into Canon cameras.
I see. Okay. So with up to the size now, for living room size, 27 feet across, I mean, in principle, you could make bigger mirrors, but it looks like we're combining those mirrors into our big telescopes. Is there any reason not to go larger, or is it it's just not necessary at this point for the next generation of projects?
Yeah, the reason to make a mirror bigger than the 27 feet we're doing now is basically the size of the freeway, because we got to get them to a mountain somewhere, and that involves both going on the freeway and up the mountain road.
You can't lift them with a helicopter? Too heavy?
I think it's too heavy. So these are 20 tons.